everyone, and welcome back. Today we're going to continue our discussion of applications of linear systems and focus in particular on one of electrical circuits and current. So in order to go into the linear algebra applications to electrical circuits, we need to first make sure we know some basic electricity physics that is associated to these problems. So let's first assume that we have a battery, and a battery typically has a positive N and a negative N. We're not going to get into terminology either, but let's assume that we have a circuit, and let's assume that we have a resistor here, and that resistor could be an appliance like a lamp or a TV or something along those sorts. So typically people assume, or at least we like to take the perspective, that electrons are going to flow from positive to negative. If you assume electrons flow from negative to positive, you're going to get the same exact answers to all of these problems, and once we start formulating these, you'll actually see why that is the case. But for our approach, we're going to assume that electrons are going to flow, for example, in that direction through that resistor, and then back towards that battery, right? And then they're going to continue flowing in that closed path. Okay, so there's a couple things in play here. For example, we have a battery which has a voltage. We have a resistor that has some resistance, which we're going to represent by R. And then we have the speed of the electrons, which we're going to refer to as I, which is going to stand for current. And the equation that relates voltage, resistance, and current is what is known as Ohm's Law. Ohm's Law. So Ohm's Law states that resistance is equal to voltage divided by current. Some people also prefer to remember this as voltage is equal to current times resistance, right? And this is actually going to be the perspective that we're going to be working with so that we don't have any fractions. So let's lay out what each of these things stand for. So V is going to stand for voltage, which is going to be in the unit volts. And then I is going to be in the, talk about current, and current is going to be measured in amps. And R is going to be measuring resistance, which is going to be in unit ohms, which is represented by Greek letter capital omega. Right? So voltage equals amps times ohms, or voltage is equal to current times resistance. All right, so let's just do a very basic example just to make sure we understand these basics. So if the voltage battery has a voltage of say 12 volts, and let's assume that we have a lamp that has a constant resistance of say 9.5 ohms, and let's assume that we have the same picture that we drew just a moment ago. So what is the current everywhere in that circuit? So from Ohm's law, we have that 12 volts V is equal to the current, which we do not know, times the resistance of 9.5 ohms. So we can simply solve this equation for I. So we have that the current at any point in that path, in particular the current across that resistor, is going to be 12 volts divided by 9.5 ohms, which is going to come out to approximately 1.26 amps, right? So amperes or amps represents the speed of an electron as it passes through the circuit. And one can show through some basic laws of physics that regardless of where you are in the circuit, in particular as you pass across this resistor, the speed of the electrons is going to be the same. In particular, the speed is going to be 1.26 amperes, right? And that's a very important thing to keep in mind as we move forward with this discussion. Now let's move into where electronic circuits start to become a little bit overwhelming to some people. So there's two basic structures of currents that people usually deal with. The first type of circuit is what is referred to as a series circuit. Okay, so let's draw out what a series circuit is. So let's assume that we have a circuit with a battery there. Let's assume that this battery is 12 volts. Let's assume that we have one resistor there. Let's assume its resistance is 5 ohms. Let's put another resistor here, and let's assume that's 4 ohms. And let's assume that we have another resistor there. Let's assume that has resistance 3 ohms. So we say that these resistors are in series because they follow on the same exact path. because notice that if an electron passes through this wire, it's going to pass through that first resistor, then it's going to pass through that second resistor, and then it's going to pass through that third resistor, and it doesn't have the option of bypassing any of them. Therefore, we say that these resistors are in series. Now, there's a theorem, which we're not going to prove here, that relates the current, resistance, and voltage of that battery, which is sort of viewed as an extension of Ohm's law. So it says this. It says that the current is the same at all points in this series circuit. That is, even though these resistors have different resistances, the resistance at this point is the same as that point, is the same as that point, is the same as that point, and the resistance across that point, and the resistance across that point, and the resistance across that point are all equal to each other. So with this, one can ask, well, what is the resistance at any particular point? In particular, for example, that point A, or that point B, or that point C, or maybe across that resistor, let's call it D, right? So since all of the resistances are the same, I just need to solve for one of them. So by Ohm's law, we know that V is equal to IR, but notice that this is going to be I times the sum of these resistances 1 through K. So that's going to be equal to the resistance across resistor 1, and then times that current times the resistance, let's call it, say, 5 ohms. And then I1, you could also call it I2, but we know that I1 and I2 would be equal, so that's going to be 4. And then we have I1, that's going to be the resistance across that particular, that current across that particular resistor, and that's going to be multiplied by 3. So since all of the currents are equal to each other, I1, I2, and I3, I've just named them I1 just for the sake of simplicity. So we have that 12 is going to be equal to 5 plus 4 plus 3, which is going to be equal to 9 plus 3, which is going to be 12 times I1. So that means I1, i.e. the current at any point in this series circuit, is going to be equal to 1 amp because we have voltages and ohms as our units, so the unit on current will be amps. All right, so that's the first type of structure that people commonly see when it comes to electrical circuits. Now the second one, which is where linear algebra actually has its highlight, is when it comes to parallel circuits. So notice for the series circuit, the electron doesn't have a choice of which resistors it passes through. With parallel circuits, we usually have a couple paths or a couple options that an electron can flow through. So let's give this a quick little example. So let's assume we have our battery here, and let's assume that this is going to be a 12-volt battery. Let's assume that our electron can go here, and then it's going to sort of branch off into two different pieces, and then they're going to sort of come together, making sure it's a closed wire. Now let's assume that is our path. On each of these little pieces, I'm going to include a couple resistors, so I'm going to include that resistor there, and I'm going to include that resistor there, and let's assume that that's our circuit. So we have a couple interesting points here, in particular these 2 points. So we know already that the current at point A and the current at point B are equal to each other, and one can also show that the current at point C and the current at point D are also going to be equal to each other as well. Now, what happens when we start splitting currents? For example, what about the current at point E and the current at point F, right? So one can guess, well, if the current at point C sort of branches off into the paths of E and F, and they have to be equal to each other at point D, then there has to be some sort of conservation of current in this particular picture, and that's exactly the case. Right. So the second theorem, again, which I'm not going to prove, is sometimes referred to as Kirchhoff's law. So the first theorem we had was Ohm's law, and now we have Kirchhoff's law, and it says this. So the current partitions, i.e. it's equally distributed, none is lost and none is gained, at branch points. So it partitions at branch points across all branches. with resistance. And you can sort of think about why I'm including this little piece at the very end here. Right? So with that being said, in this picture, that means the current at C is going to be decomposed in the current of E and the current of F in this particular example, right? So for example, if C is, for example, 10 amperes, then it's possible that that is 8 and that is, for example, 2, all right? Now I'm going to actually give us some numbers to work with here. Let's assume that this left resistor is 3 ohms, and let's assume that this is 4 ohms. Now take a guess. What current is going to be larger? Is it going to be the one with the larger resistance or the one with the smaller resistance? Take a moment and sort of think about what makes sense physically here. Right? So notice that we have 2 paths that we can travel by. Well, so let's trace out this one. So the first path is, so we travel through the top, and then we pass through the left path, pass through the 3 ohm resistor, and then we're going to pass through there. Okay, so in terms of Ohm's law, what do we have there? So from Ohm's law, we have that 12, our voltage is going to be equal to I times R, right? So let's assume that this current across here, this is I1. So 12 is going to be equal to 3I1. And if you look at the other path, so let's trace that path, for example, orange. So again, we're going to be passing through point A, we're going to get up to point C, and then instead of going left, we're going to go right, pass through that 4 ohm resistor, and then go through point B, and then back to our starting point. Keep in mind, these have to be closed loops, else the current can't pass through them. I'll give you some maybe time to think about why that is the case, but if not, let's just assume it to be true. So for the second equation, we have that V is equal to I times R, right, where R is equal to 4. Right? Now let's assume that current across resistor, let's say 2, is called I2. Right? So we have a systems of 2 equations, very simple linear equations with 2 unknowns, I1 and I2, and then from it we can see that I1 is going to be equal to 12 divided by 3, which is going to be 4 amperes, and the current 2 is going to be equal to 12 divided by 4, which is 3 amperes. Right, so what do we have here? So the current through the lesser resistor has a higher current, and the current passing through the higher resistor is going to be a lower current. So from this very basic example, we can conclude the following thing. So current flows faster along paths with less resistance. Right, and we can sort of see that here with this example. Okay, so those are the main structures associated with electrical circuits, at least with one battery, which we're not going to venture into the 2 battery or multiple battery scenarios, and also there's some other complicated structures, which we're not going to get into. So now that we know the basics of Ohm's law, Kirchhoff's law, series circuits, and parallel circuits, now let us do a more complex example combining all these to sort of see why linear algebra actually has a very strong presence in the solutions of these circuits and the currents at various points in the circuit. Suppose we have this electrical circuit given by this structure. So we have one battery on the left-hand side that's of course 40 volts, and we're going to have some electrons that are going to pass through, say, the positive terminal, through of course resistor 1, which we're going to assume has 12 ohms of resistance, and then we're going to be passing through this point, and then we get to this junction point. This junction point allows us to travel across one of 2 paths, either left or right. So let's assume that we travel across this path. We're going to be going through resistor 2, which has 5 ohms, and then once we get to this new junction point, then we can either go through 3 or 4. So for example, once we go through 3, we're going to get to this union junction point, and then we're going to be traveling across this point and then reach our destination. So that's one of the paths that we could travel. So what I like to do, just to make sure I know how many equations I'm going to have in the end, is state the number of paths that electrons can pass through. So I've traced one in blue. Another one I can pass through is, instead of going through R3, for example, I can go through R4. So that's a second path, and and another path is going to be, for example, the one at the very bottom, right? So there's going to be 3 paths for which I can go through, and the number of branch points for which I partition my current is going to be how many. So we're partitioning there, so there's 1 branch point, and then we're partitioning here, that's another branch point. So there's going to be 2 branch points. You could, of course, talk about where they sort of join back together, but you're going to realize that those equations do not contribute anything new to the system. If you do the digression equations when sort of current breaks apart instead of forms together. It's going to be the same equations eventually. All right, so our Ohm's law equations are going to be associated to the number of paths. So the Ohm's law equations are going to be associated to the number of paths, and the branch point partitions are going to be associated to the Kirchhoff's law. Okay, so Ohm's for the path, Kirchhoff's for the branch points. So let's start off with the Kirchhoff's rule. So the Kirchhoff's equations, right? So this is where the branch points sort of break apart. So I'm going to be calling I1 the current through resistor 1. We're going to have I2 the current through resistor 2, I5 that current, I3, and then I4. So it's the current through each of these resistors, right? So keep in mind I1 is also the same current at point A in this picture, and the current B is the same as the current through I2, and current C is the same as the current through I5. So keep in mind those are equal to each other. That sometimes helps people sort of to visualize what's going on here. So notice that current 1 is going to be broken down into current 2 and current 5. And then current 2 is going to be breaking apart at this particular junction point into 3 and 4. So 3 and 4. So those are 2 equations with 1, 2, 3, 4, 5 unknowns. So hopefully we can get at least 3 more equations, and then we kind of have a square system so we can solve for it. That would be ideal, right? But notice that we're going to be getting 3 equations from Ohm's law from the different number of paths, so life is wonderful. We don't have a rectangular system where things get a little strange. So from the Ohm's law equation, what do we have? So if we follow, for example, the blue path, what equation are we going to get? So V is equal to the sum of IR, right? So we're going to be passing through R1, so that's going to be 12 I1, and then we're going to be passing through 2, so it's going to be 5 I2, and then we're going to be passing through 3, so it's going to be 2 I3. If you want to pause this video and maybe list out the next 2 equations, that might be a nice little exercise. So the only difference between path blue and path green is instead of going through 3, we're going to be going through 4, right? So instead of doing 2 ohms, we're going to be doing 3 ohms. So we're going to have 40 is equal to 12I1 plus, still going through 2, but instead of going through 3, we're going to be going through 4. So it's going to be 3I4. And the last equation is going to be the red one. So we're just going to have our I1 and I5. So we're going to have 40 is equal to 12I1 plus 8I5. So those are 2 Kirchhoff's law equations and our 3 Ohm's law equations. 5 unknowns, 5 equations. Life is wonderful. So we should be able to solve this with a systems of linear equations. So what I'm going to do is I'm going to write this 5 by 5 system in a matrix equation. And what is that going to look like? So we're going to have 1 minus 1. So what I'm going to do is I'm going to move my I2 and my I5 to the left-hand side. So that's where this minus 1 is going to come from. My minus 3 and my my I4 is going to move to the left-hand side, so those are going to be negative as well. For my Ohm's law equation, I'm not even going to touch the order. So I'm going to have 1 minus 1, 0, 0, minus 1, and then 0, 1, minus 1, minus 1, 0. So you should always have only 1s, minus 1s, and 0s when it comes to the Kirchhoff's law equations. All right. Then when it comes to the Ohm's law equations, you're going to have nothing but positive numbers, and those positive numbers are going to correspond to resistances. So for example, we're going to have 12, 5, 2, 0, 0, 12, 5, 0, 3, 0, and then 12, 0, 0, 0, and 8. And then we have I1, I2, I3, I4, and I5. And keep in mind, for the Kirchhoff's law, we're setting them equal to 0, and for the Ohm's law, we're setting them equal to the voltages. Okay, so this is our equation that we seek to solve. And of course, you can try to use Gaussian elimination if you really want to, but this is probably where you want to use some software, because a 5x5 system definitely can be a little overwhelming if you try to do that by hand. So if we call this vector, for example, I, then the solution is going to be equal to approximately 2.6, 1.5, 0.9, 0.6, and 1.1 amperes. Right, so these are the currents passing through resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5, respectively, to 1 decimal place. Right, and that's how we can use basic linear systems to solve electrical circuits that have series and parallel resistances. Hope you enjoyed, and I'll see you in the next video. Take care.